Hi everybody, welcome to another HD DWF repair video. Today I'll show the repair of this Commodore PET 8032. This is another one from Mr. Lee in the UK. Unfortunately, he discovered that even the monitor PCB had issues after getting its mainboard back home. As always, the first step is a good visual inspection of the PCB. We see only two socketed ROMs, the editor ROM and the kernel ROM. Unluckily, the 6502 CPU is also socketed, so I can easily use an op generator and a RAM-ROM daughterboard if needed. During its travel to Italy, however, this board suffered some damage, like this pin in the expansion header connector that I had to straighten back. I've also found one missing screw on one of the voltage regulators. However, by carefully searching in the packing material, I found all the missing parts, or maybe almost all, since I believe there should be two washers. Anyway, I replaced the lost screw and tightened all the other ones too. We want to find -5 volts on pin 1 of any 4116 DRAM. Then 12 volts on pin 8 and 5 volts on pin 9, so all looks good so far. Then we check that we have a clock on pin 39 of the 6502. And we should find a high level on pin 40, which is the reset pin, but instead we have a low level, and this is definitely a problem. The reset circuit is very simple. UD16 on LM555 makes a one-shot boost generator. The pulse is then inverted by UE15, and finally the open collector buffer UD15 drives the reset line. So I start checking backwards. First the UD15 driver. Both the input and output are low, so it seems good. Let's check UE15 inverter then. The input on pin 1 looks definitely floating. And the output on pin 2 is low, which is correct, as a floating TTL input always acts as a logic 1. First of all, let's check that pin 3 of the 555 and pin 1 of UE15 are connected as they should. And yes, they are. Now, since pin 1 of UE15 is correctly connected to pin 3 of the 555, but still it seems unconnected, it means that the LM555 is faulty. Of course, I've also checked that pins 4 and 8 of UD16 are correctly getting +5 volts, and that pin 1 is correctly grounded. I pulled UD16, I've checked that I've not damaged any pad or trace. I've checked the other side of the PCB too, and then soldered a socket and installed a new 555 IC. The reset signal starts low at power on, then goes high, so that's okay now. And we have just a black screen. Whenever we have dead machine not starting at all, it's usually a good idea to use an op generator socket and check all the address buffers and decoders. Mr. Lee sent this NOP generator socket together with the boards to be repaired, and this has a series of LED to show the status of the various CPU signals. In this video description I've put a link to a more detailed video about the NOP generators. The first signals I'm going to check are the outputs of UD13 and UD14. These are the address bus drivers. Basically, The address bit number 0 should be a square wave at 1/4 of the CPU clock frequency, and each higher bit has half the frequency of the previous one. I'm just going to quick check all the outputs for the presence of a square wave with proper 1 and 0 levels, just forgetting about the frequency, unless, of course, I found some problems. Since there were no obvious issues with the address buffer's outputs, I'm now going to check UE12, which is the main address decoder. Each of its outputs must stay low for exactly 4 kilobytes, or in other words, 1/16 of the total address loop time with the knob generator. Let's first check that it got the correct inputs. Pin 23 looks good. 22 okay. 21 also okay. 20 looks good. 19 and 18 must be low all the time, so okay. Let's now check the outputs. Well, this is bad. Levels are too low. This one is stuck on a bad level. Yeah, another bad one. This one is bad too. So all the outputs are either stuck or have bad levels. So this IC is definitely bad. In this machine, UE12 is a Mitsubishi M53354. I believe that 0370 is the date code, so it was made in January 1970, and it's even older than me. Of course, this was a correct equivalent IC for the more common 74154, but I checked because I had rarely seen a Mitsubishi TTL IC before now. I pulled the bad UE12, checking that no parts or traces were damaged. Then I inspected also the other side of the PCB, of course. I soldered a socket and installed a Texas Instruments 74154 replacement IC. That was among a collection of spare ICs that Mr. Lee, the owner of this PET, sent together with the boards to be serviced. This IC was made in 1976, by the way. This is how the outputs of UE12 look when the decoder IC is properly working. The editor ROM can be correctly read and its content matches the good dump I have saved on my device programmer. The programmer instead has issues reading the kernel ROM. So I try to disable the continuity check and try reading again. But yes, this ROM is clearly bad, as it always outputs the same value, so I have to substitute it with one of my spare PET ROMs. Since this board is still giving a black screen, I decided to look at the CPU data bus. On the universal board PETs, almost everything is connected to the unbuffered CPU data bus. This includes all the RAM, all the ROMs, and all the input-output ICs. There is also a buffered data bus, but it's only used for video RAM access and for the expansion connector. The large number of ICs connected to the unbuffered data bus on these pads greatly increases the possibilities to have bus conflicts. In fact, here's what I found. By the way, I thought I was recording, but all I have is an unfocused picture. However, the logic high level on the data line is wrong, as it's probably held low by some IC. These bad levels were visible on all the data lines. The best tool to find shorted inputs is the current tracer, and I'm still using the knob generator on the CPU socket. I first check the I/O chips. The data bus lines are on pins 26 to 33. Let me block the LEDs to better see if the probe lights up. We get some weak indication. This is the CRT controller. But we have much stronger indication on this 6520. To be 100% sure, I'll try to inject a current on one data line with the logic pulsar. I first calibrate the current tracer sensitivity on the pulsar total current. And yes, that 6520 is getting all the current on its data line, so it must be substituted. So I removed the UB12, always checking that no damage occurred on the PCB pads and traces on both sides of the motherboard. Then I soldered a socket, and this time I try using my RAM and ROM daughterboard on the CPU socket to see if finally at least a test ROM can start. The test code suggests one of the video RAM is bad, but since the displayed characters are correct, I don't believe it's a good suggestion. Instead, notice that the last test character is flickering. That, I believe, indicates that there is still some data line conflict. I reinstalled the knob generator and I'm looking at one data line on the bottom trace and triggering on the video segment enable, which is the top trace. The first 2 kilobytes of the video segment has the actual RAM mapped, and the high level is too low, so there is a conflict. The small gap with no low level is the range from 8800 to 8FFF, where nothing is mapped, and the bus transceivers try to force always a high level. Then there are two empty 4 kilobyte segments at 9000 and 8000 that are for the option ROMs, where the conflicting IC has nothing to fight to and the data line is permanently low. And finally the not socketed ROMs at B00, C00 and D00. Interesting that the 000 ROM seems not affected by the bus conflict. I try again with the current tracer, this time on UB9 and UB10 that are the video RAM transceivers. I find high current only on pin 3 of UB10. Since I'm not yet sure about what's going on, I've decided to just cut pin 3 of UB10 and check again the data bus line D0 where this pin is connected to, and sure enough, the wrong level on the ROM axis was still present. Clearly, I'm on the wrong route, so I have soldered back UB10 pin 3 that has no real issues other than being on the other part of a bus conflict. I decided then to try another thing. The universal board PETs have this useful input called no ROM. The bar over its name means it's active when it's pulled down. When a ROM is pulled down, all the motherboard ROMs are disabled, regardless if the others will select any of them. So I grounded the no ROM line with the red wire and the clip on a 40. And yes, UD8 data 0 pin still shows some current. The high current is best seen on the PCB trace that brings the data line 0 to UD8. And of course, on the other side of UD8 there is no current anymore. So UD8 is definitely bad. The oscilloscope trace not showing a bad level when UD8 was selected should have really suggested to me that it was the real problem, but I didn't really think about that, so this is definitely a troubleshooting mistake on my side. UD8 has been pulled out, always checking that there aren't any damages on both sides of the PCB. Then I soldered a socket and installed a replacement ROM from my spares collection. Also, I think it's time to see if this machine can boot without any life support hardware. So I've also installed the editor and kernel ROMs and a spare Rockwell 6520 that was in the spare chip collection sent by Mr. Lee. Oh, looks good, so it's time to power on. And yes, we have the correct basic button. At this point, I need to connect external devices to execute all tests. However, the IEEE 488 edge connector was in really bad shape, with most of the gold layer gone. So I've decided to apply a new layer of tin to it to not leave any exposed copper. Luckily, the bottom side of the connector is still perfect, so it doesn't need any rework. Unfortunately, the IEEE 488 loopback test finds errors on all 8 data bits and on NDSC and DAV handshake lines. So let's go back to the schematics. Every IEEE 488 interface signal uses 2 port bits, one for output and one for the input. Then the 3 MC3446 ICs drive the actual bus lines with up-and collector outputs. The driver ICs, when no devices are connected to the external bus, just lock back the output pin state to the corresponding input. The test program finds errors on all the data lines plus NDAC and DAV. All these lines have either their inputs or their outputs or both going through the 6520 interface IC at UB16. It is unlikely that all the 3 MC3446 are bad, and anyway, in that case, I would expect that also ATN and RFD lines would be shown as bad. Of course, before pulling UB16, it's very wise to check that it has no missing connections on its data and bus and shake pins. Since all the other I/O chips on this PET are working fine, I don't expect that any of these bus signals has any issue. Having found no missing connections on UB16 bus interface pins, I decided to pull it. And after soldering the socket, I installed another nice Rockwell 6520 AC coming from Mr. Lee's spare chips collection. IEEE 488 problem solved now. Usually, the last step of my PET repairs is loading a RAM test program on the machine via a special cable from a PC parallel port to the PET user port. I usually do this in 2 steps. First, a basic program is loaded from tape and it's used to transfer the CBM Link machine language server on the PET. After the first transfer is done, I can simply break the basic program and execute the machine language 1 via a sys command to its stored address. We should normally get back the flashing cursor immediately, but this PET just freezes until it's resetted or power cycled. In my experience, if it was an interface issue, the transfer will never start or end correctly. Since the basic program uses only the first 16 KB RAM bank and the machine language 1 is instead loaded in the upper RAM bank, I strongly suspect a RAM issue on the upper 16 KB. Let's see if the machine language monitor gives us a clue. I want to display the RAM content from just before the end of the first 16 KB bank to just after the beginning of the second bank. So let's say from 3FF0 to 4080. And yes, look at all the AA hexadecimal on 3F rows, which is bank 0, and instead the many A2 values we find on some of the 40 rows that belong to bank 1. Let me explain what happens here. To determine the amount of available RAM, the BASIC of the PET first writes on the RAM address range the hexadecimal value AA, which is in binary just 1 and 0 alternating 4 times. After writing on all the available 32 KB address range, the BASIC code reads back the memory from the beginning and stops as soon as it reads a value different from AA. In this case, however, the basic 3 bytes are always counted to the top 32 KB. I think that the baud RAM IC holds the correct value for just enough time to allow the memory test routine to complete. Then the bits start flipping. In fact, with the machine language monitor, we found the value A2 instead of AA on some location of the upper 16 KB. The difference between AA and A2 is only on bit number 3. So we go on the RAM schematic and look for the IC connected to the bus line D3 and belonging to the upper RAM block, which is composed by the ICs getting selected by the CAS1 line. Our problematic IC is then UA12. UA12 was then cut away pin by pin to avoid any possible damage to the PCB, and each pin removed separately. Socket was soldered in its place and a non-good 4116 IC installed. If we repeat the same memory dump as before, we now get all AA values as expected. This time, when executing the machine language CBM link code, it gives back the basic prompt as it should. I can now transfer the memory test program, which is a very fast process now. And finally, let this test run for about 1 hour. This PET 8032 motherboard did not show any other problem during the last test, so it was shipped back to its owner. This board so far had the longest series of faults I had found in all my PET repairs, and surely it was an interesting troubleshooting exercise for me. I hope you enjoyed this repair video and that you learned something new. If you have any question, please use the comment section below. I hope you'll come back to my channel in the future, and that's all for now. Thank you for watching.